Welcome to ECE 761, lecture number 10, Dynamics of a two-link arm. Now, the previous lecture, we looked at coming up with the Lagrangian dynamics for a system. This is going to look at the application of finding the dynamics of a two-link robot arm. We'd actually like to find the dynamics of a three-link arm, but that's about a 10-page derivation. So just to keep things manageable, we'll just do a two-link arm. In this case, we'll define X and Y, and it's a robot. The lengths are 1 meter long. Q1 is the angle relative to the y-axis. Q2 is the angle relative to Q1. Each arm has a length of 1 meter, and each arm has a mass of 1 kilogram at the tip. The first step is come up with the dynamics for the robot. The X position is sine theta or minus sine theta. Y1 is cosine theta. Position 2 is, there it is, x1 minus sine of theta 1 plus theta 2, cosine theta 1 plus theta 2 for y, and their derivatives. Or using a shorthand notation, S1 means sine of theta 1, S12 means sine of theta 1 plus theta 2. So these are the positions and velocities of these two masses. Using that, I can now find the kinetic energy. Kinetic energy, the first mass, is 1/2 mv squared. Substituting in for x1 dot and y1 dot, note that I get a sine squared plus cosine squared, which is 1. So the kinetic energy is 1/2 theta 1 dot squared. Mass 2 is where it gets kind of ugly. It's 1/2 mv squared. The position, or velocity mass 2, is cosine theta 1 dot plus cosine theta 1 theta 2, so on. Velocity of y2 squared. Multiply it out, and you'll get cosine squared plus sine squared is 1. Here's another cosine squared plus sine squared is 1. And these two, I can use the trig identity. The trig identity is that let's see, sine A sine B plus cosine A cosine B is cosine A minus B. And that's this guy right here. So that's going to be cosine of theta 1 plus theta 2 minus cosine theta 1. Gives you just cosine theta 2. So all that simplifies out to the kinetic energy of the second mass is here. And potential energy is just mgy. Y is cosine theta 1 plus cosine theta 1 plus theta 2. So we now have the kinetic energy and potential energy. I can form the Lagrangian. So these are the Lagrangian, the total energy in the system. Using the Lagrangian, I can now find the torques. The torque on the first link is the full derivative with respect to time of the partial of L with respect to theta 1 dot minus the partial of L with respect to theta 1. Partial of L with respect to theta 1 dot. Here, everything that's not theta 1 dot is a constant. So 1 is a constant, cosine theta 2 is a constant. Here's the theta 1 dot. Gives you 2 theta 1 dot times 1 plus cosine theta 2. Ignore, there's no theta 1 dot. Here's the theta 1 dot. Gives you 1 plus cosine theta 2 dot, and no theta 1 dots of 0. So here's the partial with respect to theta 1 dot, minus the partial with respect to theta 1. Again, no theta 1s, no theta 1s, no theta 1s. There's the theta 1. Gives you minus 2g sine theta 1 plus g sine theta 1 2. Now take the full derivative. That gives you, from the chain rule, derivative of the second term, theta 2 double prime, plus derivative of the first term. Derivative of 2 cosine theta 2 theta 1 dot is 2 minus 2 sine theta 2 theta 1 dot times theta 2 dot. That's the partial with respect to theta 2 times the partial theta 2 with respect to time gives you theta 2 dot. Over here, derivative of the first term gives you a minus sine theta 2 dot times theta 2 dot gives you theta 2 dot squared. So here's the torque with respect to the first joint. Torque with respect to the second joint. This is the Lagrangian. Take the full derivative of the partial of L with respect to theta 2 dot minus the partial vel with respect to theta 2. Partial vel with respect to theta 2 dot is ignore, there's the theta 2 dot. Gives you theta 2 dot, and here's the theta 2 dot. 1 plus cosine theta 2 theta 1 dot. So there's the partial with respect to theta 2 dot. Minus the partial with respect to theta 2. And here's a term. Gives you minus sine theta 2 theta 1 dot squared. Here's another one. Minus sine theta 2 theta 1 dot theta 2 dot. And here's the theta 2. Plus g sine theta 1 2. Now take the full derivative. Gives you theta 2 double prime. Chain rule. Derivative of the second term plus derivative of the first term. And that gives you a theta minus sine theta 2 dot theta 1 dot. And this term simplifies. Here's the torque on the second joint. So the net result is here's the torque on the first joint, torque on the second joint, all functions of acceleration, velocity, and position. Typically in robotics, these are grouped. If I bring all the accelerations to one side, I get this term. This is the mass matrix. Times acceleration is the torque. Take all these product terms. Those are the Coriolis and centrifugal forces. And the gravity terms, here's gravity. And note that when well, anyway, that's the dynamics of the robot. With that, I can now simulate it. This is the code 2-link dynamics, and basically this is the same code I had up here. Given the angular velocities, and torques, in this case it's going to be 0 for free fall, I can calculate the inertia matrix, the Coriolis forces, gravity forces. Here I added 0.002 just to avoid it being singular. Once I have these, I can find the acceleration is the inverse of the mass matrix times the torque plus the Coriolis forces plus gravity forces, and that's the acceleration. And there's two MATLAB routines for that. This one is the 2-link dynamics. Given angle, velocity, and torque, calculate the acceleration. And to see if it works, this is 2-link. All it does is let the robot move freely. The torque is set to 0. Once I find the acceleration, integrate to get velocity, integrate again to get position, and then plot the robot. So this is what it looks like in free fall. Start set at 0 position. In this case, 0 position is facing the x direction. And this is a chaotic system. The energy is constant, but the energy is transitioning from mass 1 to mass 2, from kinetic energy to potential energy. That's a 2-link arm in free fall. So that's lecture number 10. The homework assignment is to repeat. If I change the mass of the robot arms, now find the dynamics. And the procedure is kind of what we did in the lecture notes. To find the position, velocity, kinetic energy, potential energy, and then start taking full derivatives and partial derivatives, and that gives you the dynamics. And that's lecture number 10 for 761 Robotics.